Electrical control of spin currents in graphene via ferroelectric switching, a European research collaboration, has demonstrated a novel method for controlling spin currents in graphene using a ferroelectric monolayer of indium selenide, in 2C3. This approach, validated through first principles and tight binding simulations, reveals that switching the polarization of in 2C3 can reverse the direction of spin currents in graphene, effectively creating an electrical spin switch. The discovery marks a significant step toward energy-efficient, non-volatile spintronic devices that do not rely on magnetic fields. The rise of spintronics and graphene's potential for 2 decades, spintronics has been a leading frontier in nanoelectronics, aiming to leverage the spin of electrons to carry and process information. Unlike traditional charge-based electronics, spin-based systems promise substantial reductions in power consumption, heat dissipation, and faster operation speeds, alongside non-volatile data retention. However, achieving precise, low-energy electrical control over spin currents without external magnetic fields has remained a major obstacle. Magnetic manipulation, while effective, presents challenges for scalability, efficiency, and compatibility with semiconductor technologies. Two-dimensional 2D materials, particularly graphene, have emerged as a potential solution. Graphene's exceptional electronic mobility and long spin relaxation time make it a prime candidate for spintronics, but its weak spin orbit coupling limits direct spin control. Heterostructures and ferroelectric control to overcome graphene's limitations, researchers have turned to Van der Waals heterostructures, stacking graphene with other 2D materials to induce new functionalities through proximity effects. Coupling graphene with ferroelectric materials, which have a spontaneous electric polarization controllable by voltage, is particularly promising. When a ferroelectric material contacts graphene, its electric dipole breaks inversion symmetry at the interface, potentially allowing spin orientation via pure electric switching. The new research introduces a graphene slash in 2C3 heterostructure platform where the ferroelectric polarization of in 2C3 modulates the spin orbit coupling in graphene. Simulations show that flipping the polarization reverses the sign of the Rashba-Edelstein effect, switching the chirality of spin textures and the spin current direction, all without magnetic fields and with minimal power consumption once the polarization is set. Key findings. Spin control via ferroelectric switching. The research team investigated graphene slash in 2C3 heterostructures in both aligned 0 degrees and twisted 5 degrees configurations. Detailed electronic structure calculations revealed that reversing the ferroelectric polarization of in 2C3 reverses the charge-to-spin conversion coefficient, creating an electrical chirality switch for spin currents in graphene. At 0 twist, the system exhibits a conventional Rashba-Edelstein effect, RE, where a charge current generates a transverse spin accumulation aligned with the ferroelectric polarization. At 5 degrees twist, the system transitions to an unconventional Rashba-Edelstein effect, URE, where the spin current becomes nearly collinear with the charge flow due to a novel radial Rashba field, previously inaccessible in planar graphene systems. Implications for future spintronic devices. These findings provide a theoretical foundation for graphene-based spin transistors controlled by ferroelectric switching, potentially enabling next-generation spin logic and memory devices with low energy consumption and high speed. The study highlights the promise of integrating 2D ferroelectric materials with graphene to unlock new spintronic functionalities. Future research should focus on experimentally validating these results to fully realize electrically controlled, non-volatile spintronic devices. The ability to manipulate spin currents without magnetic fields represents a critical step toward more efficient and scalable spintronic technologies.